everyone, so here is your intro to Riemann sums. I realize that we just did antiderivatives, and what I'm about to talk about might seem totally unrelated, and it's going to seem totally unrelated for about 2 or 3 days until we learn enough about Riemann sums to connect it all together. So for now, just remember how to do antiderivatives, and remember we add plus c at the end of antiderivative, and learn what I'm doing with the Riemann sums, and very soon we're going to connect the two because they are very closely related. In the antiderivatives video, finding the antiderivative, which is basically the same as integrating. So in that video, I said that the most common use of these antiderivatives is to find irregular areas or the area underneath a curve, finding irregular volumes. So if you have like a water bottle that's not a regular shape, you could find the volume of it, finding position, finding the average value of numbers, finding accumulation, many more things. So when I say area under a curve, I mean if I have something like that and you wanted to find the area underneath it from one time to another time. That's when you would use an integral. Those are the most common uses of it. So we've done many months of derivatives so far, basically slope of a tangent line. We're now about to start integrals, which is area under a curve most commonly. And those two are going to seem very unrelated. There's a very famous theorem, the fundamental theorem of calculus, which will connect those, but they seem unrelated right now. They are actually very closely related because they're both found using limits. Remember, the formal definition of a derivative uses limit. The limit as h goes to 0 or the limit as x goes to a. And also, these two processes, differentiation, finding a derivative, and integration, finding an integral, they're inverses of one another. So they undo each other, just like multiplying and dividing would undo each other. So let's look at a key relationship here. I'm going to set this up, but I'm not going to tell you the answer or actually do it out for you because I want you to do it out. Make sure you have all this stuff written down here. In your notes, you're going to set this all up and actually do it. And then in your groups on Monday, you're going to compare and we'll continue on from your Riemann sums notes. So let's take this position function, s of t is t squared, a basic parabola here. Let's say we have a particle moving along the x-axis back and forth, and the position of this guy is given by this position function t squared. I want you to find how far did the object move from the first to the second second. So first I just want you to show work. It's going to be real quick, easy work. Then after you show your work, underneath that, I want you to do a decent sized graph, an accurate graph. And I want you to graph time and position. I want you to graph this for the first 3 seconds. And it's going to be very easy to graph because we've graphed parabolas many times before. Then, what I want you to do, oh shoot, this always happens. I want you to draw or to find the velocity of this position function. So do the derivative, and in your notes, say v of t equals blank. Then I want you to do another grid in your notes, a graphing grid underneath this guy, t v of t, like that. And what I want you to do is graph the velocity again for the first 3 seconds accurately. That means you have a scale on your y-axis just like you did here. And I want you to find the area underneath the curve, and I say curve because it's not actually a curve, for this case at least. Find the area under the curve from 1 to 2 seconds. So whatever the graph is, find the area between the x-axis and the line itself. And there's a very important relationship between your answer here, when you found the total distance traveled, and here, when you find the area under the curve. And I want you to write it here. So basically state what you found. That is a very key relationship here in physics and in calculus. So take a minute and do that. Pause the video for a second. Based on what you just found, what this is going to mean is that if we have an object moving at a constant velocity, and we're looking at a velocity graph here. So constant velocity, in order for the velocity to be constant, it'd have to be just a straight horizontal line. If it wasn't horizontal, then the velocity would not be constant. So if we have just a constant velocity, it's really easy to find the area under the curve, which basically is the distance that the particle has traveled, just using geometry. So let's say I have a particle moving at 7 and this is in seconds, and this is in meters per second. If I want to find how far this guy is moved from the first to the third second of its movement here, 1 to 3, all you have to do is find the area under the curve. And again, when we say curve, it can mean line or a curve. You just have to find the area under it. So 2 times 7, obviously 14. You could have done this many years ago just using distance equals rate times time, that formula. But the connection with calculus is it's going to involve integrals very soon. Another thing that is going to be very important is units here. So 2 is along the x-axis. That was in seconds. And 7, that was the velocity here, is meters per second. Units are going to be your best friend here when we get to the more complicated problems. Whenever you multiply these, the units cancel, leaving you with meters, which is why the area under the curve of a velocity graph will give us the total distance traveled. Now, I'm going to give you one more quick example. Let's take a function or a particle, and its velocity can be described using this graph. It's changing velocities very, very abruptly, like within not even a second. Now, this is not very realistic because nothing can change from 5 to 10 meters per second with no time elapsed, but let's just assume that this is okay. I want you to find the total distance traveled in the first 8 seconds, and it's just going to be quick. I want you to use geometry. So just show your work here, how you got that. We'll compare that on Monday. We're going to be practicing geometry for a couple days before we get to the actual calculus part of it. And the lead-in to Riemann sum, so you're about to go watch the actual Riemann sum notes problem, is what if we have a velocity function that doesn't look like this? It's not a nice one with straight lines. What if we have a velocity function, and most of them are not going to be nice ones, time and velocity. What if we have a function that looks like this, and that's its velocity? How on earth are we going to find the total distance traveled, meaning find the area under the curve? Find the area under the curve, because there's no geometry formula for this area. It just doesn't exist. This is where Riemann sums come into play. We talked about this on the first day of school when I had you find area or find the volume of something that wasn't regular. We're going to do something that involves splitting it up into skinny rectangles, many skinny rectangles, so that we can get the best approximation to the height that we can. That's basically what the next video, the Riemann sums notes, is about. There are 3 different ways to do this. All are needed on the AP exam. Actually, in BC, you're going to have to learn a 4th way as well to approximate by splitting it up. But at this point, just realize that the reason you have to learn Riemann sums is because we want to approximate areas under a curve, and we can't use geometry to do it, and we're very soon going to connect it to integrals and to derivatives. All right, so make sure you get all this down, make sure you've answered all the questions in the video, and you can then move on to the Riemann sums. All right, and I will see you Monday.